Well, video 2 of our geometric vector proofs, and we're getting stuck into an example. So prove that if the diagonals of a parallelogram are of equal length, then the parallelogram is a rectangle. So we start by drawing a diagram. It's up to you whether you want to draw a rectangle or a parallelogram. For this one, because we're going to prove this, maybe just make the lean on it just fairly subtle, if you know what I mean. So now we've got diagonals, so we're going to put them in. And let's name some sides here. So here's a hint: always name one of the vertices 0 or O for origin, because we're talking about position vectors. This concept of position. So position vectors are in reference to an origin, and use some convenient letters elsewhere. So we have OABC. Okay, so we've got to prove that if the diagonals are of equal length, then it's actually a special case of the parallelogram. It's a rectangle. So let's assume that the diagonals are of an equal length. So the diagonals are OB and CA. So putting it in vector form, make sure you put the directed arrow symbol above the OB. Same with CA. You can see there our two diagonals. So that would mean that. Now, before we go any further, the position vector here, OA, we are going to, so you can imagine there's like a little arrowhead there. We're going to give that a second name, lowercase a with the tilde, and OC, we're going to call that lowercase c too. It's quite handy to use the other notation as well. Now the idea here is to get expressions for OB and CA in terms of lowercase a and lowercase c. So now OB, the vector OB, not its magnitude, the actual vector, the vector OB can be written using geometrical vector addition as OA plus AB. So we know, because it's a parallelogram, that the bottom side and the top side are parallel, and they're the same length as well because it's a parallelogram. We can replace AB with OC. It's the same vector, just translated in a different place. Now remember how vector addition works. We can do that. We can translate the vector and put it head to tail. So if we put this vector here head to the head of OA to the tail of that OC vector, it would be the same as adding the AB on. So they're equivalent statements, and the good thing about that is that they have these other names. So OA is lowercase a and OC is lowercase c with the tilde. Now we're getting a few statements here, so I'm going to just number them just so we can refer back to that. That was first significant statement 1, 2, and another thing we need to look at is an expression for CA. So we've got an expression for OB, not its magnitude, we've got an expression for the vector. CA, we can get that by going negative of this vector here, which puts the direction in the opposite direction, the arrowhead in the opposite end of it. So we can say that it's negative of OC plus OA, which is negative C plus A in lowercase, which is the same as A takes C if you understand your vector addition. So that's going to be statement number 3. So going back to statement 1 above there, we can square both sides. The magnitude of vector OB squared would have to equal the magnitude of vector CA squared, because the magnitudes equaled each other, so if we square them, they're equal. And that's statement 4. Now what we're heading to is, because we've got to prove that it's a rectangle, the angles are equal to 90 degrees. Okay, so that stops from being any other sort of parallelogram and makes it a rectangle, and that's what we're heading towards, and that's why we're looking at squaring things for reasons you shall see. And we're going to employ the dot product too, because remember, when the dot product is 0, or the scalar product is 0, okay, we have perpendicularity there, and that's where we're heading, and that's why we've got squareds happening. You'll see in a minute where I'm taking this. And remember from our previous work that if we've got x dot x is the same as the magnitude of x squared, so the magnitude of OB squared would be vector OB dotted with vector OB, which is the same as, let's go back up for that expression we had back there. OB statement 2 says it's the same as A plus C, so to be A plus C, which is a vector dotted with itself, and we can use our law of distributivity of scalar product or dot product. You can call it dot product or scalar product. That's from our previous work, which means that it's very much like you see with real numbers. So a bit like that FOIL, if you've seen FOIL with your regular algebra, first, outer, inner, last. So we have A dot A, first by first, plus, whoops, error, fixed, okay, and then second by first, and so on. Okay, and using that same knowledge from above, that would be, now there's two lots of the same thing. Remember, vectors are also they're commutative by the dot product. Okay, so commutativity of scalar product and that means it's like two lots of A dot C, because this one here can be looked at the other way around. Okay, so remember what commutativity means. So we've got 2a dot c and keep that out of the way, plus c dot c is the magnitude of vector c all squared. On the right hand side we need to use what we found in statement 3 above. So CA is vector A lowercase minus C, and that'll be dotted with itself just like above on the left hand side. Same process, so I'll go a bit faster this time. So just be careful of our signs. Same as above. At least this forces you to revise some of your vector work. Now we have two more results. What number are we up to? 5 and 6. So that would be result 5, and that would be result 6. Okay. Result 4 said that those two things are equal to each other. So these last two results, 5 and 6, are equated, and thus we've got those two things equal to each other. That's not as horrendous as it looks. Persevere, you'll see that things get a little bit cleaner from here on. And writing all that in. So we can subtract like things from both sides. So that, subtracting those from both sides, then we end up with 2a dot c equals negative 2a dot c. So we need to add 2 lots of a dot c to both sides, which makes 4a dot c on that side and 0 on that side. Divide through, well, multiply by a quarter, a scalar of a quarter on both sides. We don't divide it with vectors. So we got a dot c equals 0. Now that means they're perpendicular. So that means that on that diagram, angle COA, for example, equals 90 degrees, and because it's a parallelogram, the opposite side will be 90. So that means that parallelogram is a rectangle. If you think about that, it's a rectangular, whoops, she's a rectangle, because if you look back at the diagram at COA, we've shown as 90. So if that's 90, then that will be 90, and you have 180 degrees out of 360. So we have 180 degrees left, and A and C being a parallelogram are the same too. So all angles must be 90. So there we go, we've shown that it is a rectangle. And the last thing we used there was the perpendicularity. So I'll just put that in. QED, finito.